Hello folks, you're listening to Live Mike, and I'm joined by a very special guest today. Today I have something that will challenge your understanding of the workings of the universe. Dr. Robert Sungenis, a prolific author, is a pioneer in the research of geocentric cosmology. He has co-authored a 3-volume work entitled Galileo Was Wrong, the Church Was Right. Volume 1 deals with the scientific case for geocentrism. Volume 2, the historical case for geocentrism. Volume 3, the evidence from church history. Galileo Was Wrong, the Church Was Right is one of the most unique and penetrating books you will ever read. Authors Dr. Sungenis and Robert Bennett take you on a tour of science and history, the likes of which you would have never believed possible, unless it were told to you in detailed and graphic form. Has modern science led us down the primrose path and convinced us of something that they cannot prove, and that is, in actuality, false? Were the fathers of the church, the medievals, popes, and cardinals of the 17th century correct in believing that the earth, based on the face value reading of scripture, was standing still in the center of the universe? Come with an open mind and allow these two authors to show you facts and figures that have been hidden from the public for a very long time. This page-turner that you'll find hard to put down once you get riveted by the astounding material these authors have assembled for you. Prepare yourself, however, when reading this. Your world will be rocked, literally and figuratively. All right, here he is, folks. Dr. Robert Sungenis. Welcome to MSI Radio. Great to have you with us.
Hi, Michael. I'm privileged to be on your program, and I hope that the next 3 hours is going to be rewarding for everybody who's listening. And I want to back up what you said by saying that I was astounded by this 10 years ago. I had made that fateful decision on the Internet where I saw someone talking about a geocentric universe, and that fateful decision was to either click to find more information or to bypass it and go on to the next topic. And lo and behold, I clicked, and there I found a PhD in astronomy talking about the fact that the Earth was in the center of the universe and not moving. And I, like everyone else who were first introduced to this kind of thing, laughed and thought the guy was, either not all there or was making a lot of money with some sensationalism or whatever the case may be. But I do know some physics because I was a physics major in college, and so I began to read some of the material, and from a physical, scientific standpoint, it made a lot of sense to me. I wasn't, anywhere convinced that he was on the right track, but at least he had my attention. And I figured it deserved a little bit more attention, and I began to study it. That was 10 years ago. Since then, I've, as you said, written the 3 volumes, and those volumes amass to 2,400 pages. And we are also making a movie, and that movie is called The Principle, and that will be coming out probably in February or March of next year. And it deals with this very topic, but in a very entertaining and educating way. And we hope to get it in theaters, and we're looking very much forward to it. And
you have some real heavy hitters in that film, don't you, Doctor? Captain Janeway from Star Trek Voyager is the narrator, and people that worked on the life of P, Thor, for the graphics. One fellow that worked on The Passion of Christ and March of the Penguins as your promoter. It looks like you got really something there that's going to be worthwhile. Looking forward to it.
Yeah, and we've also got the top cosmologists in the world being interviewed on our movie. So these are people that, if you've watched the Discovery Channel or National Geographic or History Channel, you've seen these faces on TV many times. So people are familiar with them. We've got them all interviewed, and we have high-end graphics, we've got high-end music, we've got a great narrator. So yeah, this is big time. You know, this is not your mom and pop type of movie you just pop into DVD. This is going to be a theatrical release with the DVD following, but this is highest quality movie we can make.
Doctor, could you just explain to this audience what exactly is geocentrism and what are the mechanics of geocentrism?
Well, geocentrism, by the name of the word geocentric, means that the geo, the Earth, is in the center of the universe. And in addition to that, it also means that the Earth is not moving, because whatever occupies the center, let's say you draw a circle, if you put a dot in the center of that and you rotate the circle, well, the dot stays where it is, you see. So in that sense, geocentric usually carries the connotation that the Earth is not revolving around the sun and it is not rotating on its axis. The universe itself is rotating around a fixed Earth. So that's about as geocentric as you can get. Now, someone might object and say, well, how can that be? Well, you can use Newtonian, Machian, Einsteinian physics and show that mathematically speaking and scientifically speaking, it's just as viable to have an Earth fixed in the center of the universe with the universe rotating around it as it is to have a fixed universe and the Earth underneath of that rotating within it. Both of these are viable and scientifically allowable explanations of how the universe works. It just so happens that only one of them is taught in our grade schools, high schools, colleges, and universities. And that is because we are in the throes of what we would call the Copernican revolution. That is, that there is a bias, if you could call it that, or a favorite view of cosmology that says that Copernicus was, of the two, since we know that both are viable, of the two, which one do we prefer? They prefer the Copernican view, and that's called the Copernican principle. And that is that the Earth is nothing special. It's out in the remote recesses of space. It has no rhyme or reason to it. It all got there by chance. And we don't know exactly where we are in the universe. All we know is that we're here. And we're nothing special because we all came from the stars when they exploded. And the very atoms in your right hand may be different than the atoms in your left hand. They may have come, in other words, from two different places, because it was all the product of a big explosion 13.7 billion years ago in this thing called the Big Bang. And we're out here, and there's no one to take care of us because we got here by chance, and we're nothing special. All that I've just described is the Copernican principle. And that is the dominant view that you find in all the physics textbooks, astronomy textbooks throughout the world. And that means that every piece of evidence that comes in the telescope will be interpreted through the grid of the Copernican principle. That is, that philosophy has a large part in the interpretation of scientific data. And this is not just my idea. This is an idea that was propounded by George F.R. Ellis, one of the premier physicists in the world today. He teaches at the University in South Africa. He said that I can make for you a model of the universe where the Earth is in the center, the universe rotates around it, and you could not argue with me on scientific principles that it is invalid. The only thing you can do is object to me on philosophical principles. And what he's saying basically is that you can make the math, and that's how scientists talk to each other, through math. You can make the math such that you can have the Earth in the center and the universe rotating around it, or, as I said before, you can have the universe fixed and the Earth rotating within it. Either one, the math can support. And so the question is, well, how are you going to choose? Well, as I said before, they choose based on their philosophical bias. That is the Copernican principle. And so every piece of data, again, that comes in that telescope, they're going to interpret through the Copernican principle, wherein they will not allow the Earth to assume the center position, the special position in the universe. They want it to remain remote, in recesses of space. And the question would be, well, why do they want to do that? Well, it's not too hard to reason why. Stephen Hawking, for example, said that he knows that if you take the science...
I'm sorry, is this reference to page 47 of his best-selling book, Brief History of Time?
Yes, it is.
Mm-hmm.
Yes. People can pick that up for themselves. Between pages 42 and 47, he goes into this. And he says that when Edwin Hubble saw the galaxies with their redshift back in 1929, it was amazing to him because everyone expected the galaxies to have blue shifts and red shifts, not just red shifts. Now, red shifts, if you are familiar with the term, or if you're not familiar with the term, is I can explain it very simply. Redshift is the tendency of the white light to go to the red end of the spectrum. And if it's going to the red end of the spectrum, let's say you see a rainbow, and the rainbow looks more red, the reds are more prominent than the other 6 colors. Well, that means something. That would mean that the rainbow is actually moving away from you at a very high speed, and the wavelength of the light is being stretched, so you see more red than you would see blue or violet. And if that's the case, when you're looking at the galaxies, well, that means these galaxies are moving away from us, or the other possibility is that they're losing energy as the light is coming from the galaxies, and Hubble also admitted that. But let's just say it was that the galaxies were moving away from us. Well, if we look around us and in every direction we see red, a red shift, that means there's no blue shift. Well, that means we're in the center of the dispersion. We're in the center of the expansion. And Hubble saw this in his telescope, and he didn't know what to do with it, but he knew the implications of it. The implications of it were that the Earth is in the center of the universe. And he remarks in his book, the 1937 book called Observational Approach to Cosmology, on pages 50, 51, 52, 54, 60, and 63, that the option of having the Earth in the center of the universe is a horrible option. It is a option that we must avoid at all costs. It is an option that is intolerable. These are all his words that he uses in his book.
Very scientific words.
Yeah. And you're wondering, well, why the emotional reaction here? You know, what is it? I mean, aren't you a scientist? Shouldn't you be amazed at this kind of evidence if that's what you see in your telescope? Well, what it tells us is that Hubble, like everyone else, has a philosophical bias, and that is he doesn't want the universe to have a center point. He doesn't want the Earth to be in the center of the universe. And the reason why is this. Philosophically, if you have an Earth in the center of the universe and the whole universe is rotating around it, that means the Earth has the dominant position, but more so is that someone with a capital S had to put it there. Because it's not going to happen by chance, you see. That's the implication of having the Earth in the center of the universe, and that's an implication that Hubble knew he could not accept. Now, going back to Stephen Hawking, in his book, A Brief History of Time, he's remarking about what Hubble saw in his telescope, and Hawking admits, he says, well, it is true. If you saw the galaxies all around you, and no matter what direction you looked, you saw them having a redshift, well, you would think, yes, that we're in the center of the universe, because you couldn't have a redshift in every quadrant of the sky if we weren't in the center. It just makes sense. So he says, but we can't accept that. Okay? Now and then he goes on to say, well, we have no scientific reason for not accepting it. And then he goes in the next paragraph and he says, well, here's the reason I can't accept it. He goes, because I want to be modest. I want to be modest. In other words, he's saying, if I allow the interpretation that puts the earth in the center of the universe, well, that means I'm looking at the human race as some special creatures in the universe, and that's a prideful position. And so I don't want to be prideful. I want to be modest, so I'm going to take the earth out of the center, and I'm going to try to figure out a way that I can interpret the redshift in these galaxies as something other than the earth in the center of the universe. And what they came up with was what Hubble had suggested back in 1929. He said, well, if we do this, if we change the dynamics and the dimensions of space, and we make it as if it's a balloon, and we put ourselves, that is our galaxy, the Milky Way galaxy, on the surface of that balloon, and all the other galaxies on the surface of that balloon, so that there is no center. It's just a balloon surface, and you can do this with Riemann geometry, where they call it a hyperspace, where you can have the space curved in such a way where you just have a balloon surface with no with no central point and no substance beneath that surface. And so if we put all these galaxies on the surface and we blow up this balloon, just like you would blow up a balloon at a party, well, what happens to that balloon? Well, the balloon starts expanding, you see, and all the dots on that balloon, all the galaxies, so to speak, would be separating from each other by the same rate. He goes, so that's how I can explain away putting the Earth in the center. I'll just put the Earth on the surface of this balloon and we'll blow it up, and we'll call this the Big Bang expansion, you see, and that'll take the Earth out of the center. He goes, and now that's the explanation I prefer, but I don't have any scientific proof for it. I just prefer it because I want to be modest. Now I would come back and say, well, that's a feigning of modesty. That's a feigning of humility. It's not real humility. Real humility would be to say, if I find evidence that puts Earth in the center of the universe, well, that means that someone greater than me put it there, because I know it can't happen by chance. And if I really want to be humble, then I'll humble myself before that someone, with a capital S, and I will submit to him. And I will try to find him. I will look at the universe in a totally different way now and see that it was put there by design, not by chance, you see. That's really being humble with the evidence. So I don't accept what Hawking says about being modest. That's just an escape hatch that he's created for himself.
You mentioned a second ago about the substance of space. What is the aether, if I'm pronouncing that correctly?
Yeah, ether.
Ether.
It's spelled in two different ways, E-T-H-E-R or A-E-T-H-E-R. This is a concept, it goes all the way back to the Greeks. The word atom comes from the Greeks. Atom means indivisible. They had a concept where you could keep cutting matter. Let's say you had a ruler 12 inches long, and you cut it in half to 6 inches, then you cut it in half again to 3, and then again to 1.5 inches. Well, theoretically, you could go down until you have this point of matter that there's no return, so to speak. You reach a point where the Greeks knew conceptually that there had to be the smallest substance that could not be divided again, and they called that the atom. They also had the concept of the ether. That is, though material objects have are composed of atoms that you reach a point where they're indivisible, so the space does also, and they called that the ether, where it reaches a point where you can't divide space anymore, and the ultimate particle, so to speak, would be an ether particle. So that concept is very old. It's an ancient concept. But it stuck around because philosophically and scientifically it's hard to get away from, because you have to figure if I'm breathing air, for example, it's oxygen, nitrogen. As a matter of fact, most of it's nitrogen, about 78% nitrogen, 16% oxygen. You got a little argon in there, a little carbon dioxide. Okay, so you're picturing all these atoms in the air that you're breathing, but you can't see it, right? It's invisible. And yet you know all these elements are going in your lungs every time you take a breath. Well, the ancient Greeks and even modern scientists understood that, well, space has to have something to it. It has to have a substance to it because philosophically, nothing cannot exist.
Yes.
You have the Earth and the Moon. So what's between the Earth and the Moon? After you get out of the Earth's atmosphere, what's between the Earth and the Moon? Well, they used to call it a vacuum. There's no air up there, so it's a vacuum. If you open up a can up in outer space between the Earth and the Moon, all the air would be sucked up out of that can because it would go into this void, whatever you want to call it. It's a vacuum. But since then, in quantum mechanics, they have found that the vacuum is not really a vacuum. It's actually filled with material substance. Although this material substance they have figured out is not in the realm of protons, neutrons, and electrons, where you're down to around 10 to the minus 13 centimeters in diameter. When you're talking about the vacuum material out in outer space, you're talking about stuff that's down to the 10 to the minus 33 centimeters. That's 20 orders of magnitude smaller than the electron.
Super small.
super small. Yeah, I mean, it's so small. They give it a name. It's called the Planck dimensions. They have a Planck temperature, a Planck diameter, a Planck mass, and these are all very, very exorbitant figures that we're talking about here. But that's in the quantum vacuum now. So that's what they've discovered. So space is not nothing. Okay. Now there is a professor, however, and his name is Lawrence Krauss. He teaches at the Arizona State University, and he has a book out. I think the title is Something from Nothing, or How the Universe Came from Nothing, something like that. Just published last year, 2012. As a matter of fact, he's in our movie. We interviewed him a couple of years ago at his university. But he's trying to sell this book by saying that the universe came from nothing. But his nothing is not really nothing. What he's saying is that it appears to be nothing, but it actually is the quantum foam or the quantum domain, where you have these what they call virtual particles in the Planck dimensions that supposedly, according to him, pop in and out of existence from other universes. Now that's all garbage, of course. I don't accept any of it except the fact that the Planck dimensions are real, because quantum mechanics has discovered this as a necessary ingredient in order to understand the space that is out there. And they've actually tried to use this quantum vacuum to propel the Big Bang expansion that they need, but it has too much energy for them. It has 10 to the 120th power more energy than they need, so they can't use the quantum vacuum out there for the Big Bang expansion. And so they're stuck. And that's why they create these things called dark energy and dark matter today, because these are actually pure inventions from modern cosmology, but they need them in order to keep this Big Bang expansion alive that they had predicted back in the 1960s. And so anyway, all this stuff is related. I know I'm going into different areas here, but it's all related to this thing, the question you asked about what is space, you see. And it's not as simple as we were led to believe prior to the discoveries in the 20th century.
Okay, Doctor. Now, you mentioned a few moments ago about Edwin Hubble and the redshift evidence. How do we know, Doctor? What is the scientific evidence from experimentation and observation? Do we have to go back to the 19th century? Is that where we should begin?
Well, yeah. In regards to the issue of geocentrism, the first indications of scientific breakthrough in determining which universe was correct, the heliocentric or the geocentric. One of the first experiments done was by a French scientist named Dominique Arago in the early 1800s. Prior to that, they had debates about the construction of the universe. You had Copernicus and Galileo and Kepler on the heliocentric side. But then you had a lot of people on the geocentric side that you don't hear talked about in, grade schools and universities today because, it's just not popular. But like Tycho Brahe, was Kepler's employer. And, Kepler used to crunch numbers for Tycho Brahe, but Tycho Brahe was a very famous Danish astronomer, and he was a geocentrist. And he said that he would hold on to geocentrism because they could not find any evidence of stellar parallax in space. And I know that's a term people might not be familiar with. The stellar parallax is the phenomena that occurs when you see one star shift in front of another because the second star is farther away. And so if the Earth is moving around the sun, it'll appear as if that front star, the star that's nearest to you, is moving or shifting against the background of the star that's farther away. And Tycho Brahe, the geocentrist, said, since we don't see that, then
Doctor, may I interrupt you for just one moment? I have just provided the audience in the chat room with your website, Galileo Was Wrong. Do you remember which figure of video presentation you had to demonstrate stellar parallax so that people could look and listen to what you're saying? Do you remember which video it was? Offhand?
Yeah.
Okay.
Well, it'll have parallax on there, I believe, in the upper left-hand corner.
Okay.
I think there's only about 15 videos there.
Mm-hmm.
So all they have to do is scroll down and find the one where you have the stars in the sky and then there are lines drawn from that star or from those three stars.
I think it's the 10th one down, Doctor.
Okay.
Okay.
All right. Yeah. So anyway, I'm going a long way around to answer your question. I don't know how far back you wanted to go. Maybe you repeat that question again.
Sure.
So
I basically I just wanted to ask, how do we know? What is the scientific evidence from experimentation and observation? And then I said, should we begin in the 19th century? And
yeah. All right. Yeah. So let's go back there. We'll start with Arago. Arago looked through his telescope at a star throughout the year, and he expected that as he looked at the star, he would have to change the focus of his telescope, because if the Earth is going around the sun, then it's going to be farther away from the star at certain times of the year and nearer to that star at certain times throughout the year. And if you've ever taken a picture, if you use one of those older cameras that doesn't have automatic focus, you know that if you go further away from the person you're taking the photograph of, well, you have to change the focus of the camera, okay? And that's true in optics. Anybody will agree with that principle. So Arago had this idea, well, if the Earth is moving, then I should have to change the focus when I'm viewing the star over the course of the year. And lo and behold, he didn't have to change his focus, okay? So that meant something. You just can't take this information and say, oh, well, that's just a haphazard kind of a mistake maybe. No, if you're a scientist, you have to find out why that is the case, why your theory did not match the experimental evidence. And the implications of that, of course, are that, well, the Earth isn't moving. That's why you don't have to change the focus of the telescope. And the star is far enough away that you don't have to change the focus, because it really doesn't make, since it's many light years away, it doesn't really make any difference how that star is moving, because it's basically in the same place all the time. The only difference would be made is if the Earth is revolving around the sun, and it revolves on a 186 million mile diameter. Well, that's a pretty significant distance. It's going to require some rearranging of the focus of the telescope. And yet they didn't have to do that. So there was the first indication in the early 19th century that something was not right with theory. And so he brought this issue to one of his French scientist friends, Augustin Fresnel. It's spelled Fresnel. And Fresnel came up with this theory that the reason Arago didn't have to adjust the focus of his telescope was the fact that the ether that the Earth was carrying with it was moving the light in such a way where it would not require Arago to refocus his telescope. Now this, it sounds ad hoc, and it certainly was ad hoc because he had no way. This is just all theory. He didn't prove any of this. And then he actually put this theory into a mathematical formula, 1 minus 1 over n squared, n being the refractive index of the ether, and and claimed that it's not because the Earth is standing still, it's because of the Earth grabbing this ether and doing tricks on the light, so to speak. And so and this was like around the 1840s, 50s, 60s, Fresnel was working. And then there was another experiment done that was similar to Arago's, and this was done by a guy named George Bedell Airy, A-I-R-Y, and he was a very famous astronomer royal from England.
I thought his experiment was one of the most persuasive, in my opinion. But please continue.
Yeah, it was very persuasive. And the reason he did that was he was going to determine whether Fresnel's explanation of Arago's experiment was valid. And so what Airy did was, instead of one telescope, he got 2 telescopes side by side, and one was filled with air, of course, and the other was filled with water. Now the basis for this experiment was this: if the Earth is moving around the sun, and it's a pretty good clip, 66,000 miles per hour that it would have to be moving to complete that revolution in 1 year. So that's pretty fast. That's 19.5 miles per second. Well, if that's the case, then the light coming from a star, if it hits the water telescope, we would have to tilt the telescope, that water telescope, to the lower end of that star in order to catch the light rays to be the same as if they were going through the air telescope. And the reason for that is this: light goes slower in water than it does the air. So if that light, because of the Earth's movement, in other words, if the telescope needs to be adjusted so that the telescope gets all the light of the star, even though the Earth is moving very rapidly around the sun, well, that means we're going to have to tilt that telescope just a little bit more toward the lower end of that star to get all the light that the star has to offer. And you can compare this, for example, to when you're walking in the rain with an umbrella. Let's say that you're standing still, first of all, in the rain with an umbrella. The rain is coming straight down on you, and so you don't have to move your umbrella. You just hold it straight up and down, and you don't get wet. But let's say you started running with your umbrella. Well, what's going to happen then is some of that rain, it's still coming down straight, but as you're moving, you're actually moving into the rain, and it looks like the rain is going on a diagonal, and it's going to hit the pants or the shoes of your garments, unless you tilt the umbrella toward the direction that you're running in order to stop that rain from hitting your shoes. Okay? Well, that's the same principle here with Airy. He said, in order to catch that light, I have to tilt the telescope a little bit more, the water telescope that is, and that will prove that the Earth is revolving around the sun if I have to tilt this water telescope a little bit more toward the star. Lo and behold, what did he find? He found that he did not have to tilt that water telescope toward the star as compared to the air-filled telescope. They both had the same refraction. That is, the light is coming in from that star as if that star was right overhead, and it was coming straight in, and it went to the eyepiece of both telescopes without hitting the side of the water telescope. And that's what he expected. He expected the light beam of the star to hit the side of that water telescope, and that would prove that the Earth was revolving around the sun. But it didn't. It went right to the eyepiece of that telescope. And that means that, hey, the Earth is not moving. Because if it was moving, he would have had to tilt that telescope.
Absolutely.
And it meant that the star is far enough away that from whatever telescope you had on Earth, the light's coming straight in, you see. It's far enough away, and there's no movement underneath of it. That is, the Earth isn't moving. So, this was astounding information. They were.
I mean, it's just like, it's irrefutable. You just look at it and you're just like, what explanation can you possibly give to refute that?
Yeah, there's only one guy I found in all my research who even attempted an explanation. His name is Wolfgang Pauli. He was a very famous physicist back in Einstein's era. As a matter of fact, he wrote a couple books. And I forget exactly what he said, but it was an inane comment. It really had no validity whatsoever. But when science is silent about an experiment like that, it means something, because if it was so easy to explain, they would have been jumping all over it. As a matter of fact, the experiment was called Airy's failure. That's not how it was dubbed, Airy's failure, because he failed to show that the Earth was revolving around the sun with this experiment. So, they played with starlight a lot during the 1800s. There's a few other experiments.
Oh, I'm sorry, go ahead.
There was Martinez Hooke. He did an experiment similar. He ran light through tubes of water. Armand Fuseau, another French physicist, did the same, and he was trying to prove the Fresnel drag theory. Who else was there?
Michelson experiment. Can we talk about that one? Michelson-Morley?
Yeah, I'll get to that next.
Mm-hmm.
Yeah, then there was another experiment done by Mascar. He did experiments on the polarization of light, and the idea there was that if the Earth was rotating, then it would polarize the light. In other words, it would be twisting the light due to the fact that the Earth was turning in a circle. And he found that there was no twisting of the light. There's no polarization. So that means the Earth was rotating. I mean, there's all kinds of things that were going on. These are all documented in my book.
All these conveniently left out of contemporary physics classes today. Yes?
Yeah. Well, or if they do mention them, it's always with the Copernican principle bias, you see. Like I said at the beginning, all the data from the telescopes will be interpreted from the Copernican principle. And so it's already assumed that when Airy is putting up these two telescopes, that the Earth is revolving around the sun. And so you try to explain away why the light from the water-filled telescope didn't hit the side of the telescope by using the Copernican principle. And whatever way it comes out in the wash really doesn't make any difference to them, as long as they can convince everybody that this is the only possible explanation through the Copernican principle. And there's no airtime for the geocentric explanation at all, and which is the reason why we're here talking about it today. So back to the issue of light. So they got away from starlight. So okay, well let's go back to the laboratory. And James Clerk Maxwell had suggested this experiment to Albert Michelson. James Clerk Maxwell was a very famous physicist who gave us his electromagnetic equations. He had suggested that they do experiments on light in the laboratory as opposed to on the stars. So Michelson came up with this thing called an interferometer. And what an interferometer does is it takes two light beams and it sends them on a path. And then on the path back to the receiver, the light beams will either coincide in the wavelength or be disrupted in the wavelength. That is, the crest of one will meet the crest of the other, or the crest of one will meet the trail of the other. And if the crest meets the trail of the other, that means they're out of phase, they're out of sync. And these will cause what they call fringe shifts, F-R-I-N-G-E, shifts in a receiver that receives both these light waves coming back. And depending on the displacement of these fringe shifts, you can tell how much the waves have been displaced from one another. That is, you can tell whether wave A came back faster than wave B. All right? Now, they shouldn't be coming back faster. A and B should both be coming back fast, that's at the same speed, because light travels the same. You know, whatever way you shoot a light beam, it travels the same speed, in whatever direction you point it. At least so they thought. Okay? The idea behind the interferometer was this. If we shoot a light beam, let's call it light beam A, from east to west, okay, east to west, that's the direction that the Earth is supposedly revolving around the sun. Okay, it's moving counterclockwise around the sun, and that's from west to east. Okay, so if we shoot a light beam from east to west in the opposite direction that the Earth is supposedly revolving around the sun, then that light beam should go slower than a light beam that is shot from, let's say, the equator up to the North Pole. All right. The reason for that is if there's a resistance, let's just say the Earth was revolving around the sun and yet space was filled with air. Well, what would we expect? Well, we would expect that if we shot a light beam through that air, it's going to go slower than if we shot the light beam from the equator to the North Pole, because the light from the equator to the North Pole was not having the same resistance as the light shot from east to west. Okay, does that make sense?
It does, because one, it's not fighting against anything. It's just going in a straight line. The other is having to contend with going around the sun in the opposite direction. Is that what you're trying to say?
That's right. Okay. Yeah. And it's just like if you were in a pool of water and there was the water, you know, what do they call those pools where the water automatically is creating a wave for you? You can go surf on them and all kinds of.
A wave making machine?
Yeah. Mm-hmm. You know, so if the water is moving towards you, now if you're in the pool, well, there's a certain resistance now. That water is going by you, so there's a certain resistance. And if you shot a light beam in that water that was moving towards you, it would go slower than if that water was going the opposite direction. Okay? Because there's a resistance there. As a matter of fact, that's what all these other experiments in the 1800s found. Martinez Hooke, and a few others found that light was slower in water that was going the opposite direction. So, if space is filled with ether, which is a substance, well, that means that a light beam shot from east to west in the opposite presumed revolution of the Earth, well, that light beam would go a little slower than one shot from the equator to the North Pole. So this is exactly what Michelson's experiment did. He did the first one in 1881, and he shot. What he had is he had a table, and the light beams would go back and forth, and then he shot perpendicular light beams across those, and so you had basically light beams going at a 90-degree angle. And he found that when he rotated the table to try to make the light beams coincide with the revolution of the Earth, he found that there's no difference in the light beams traveling east to west as opposed to those going from north to south or south to north. And this was disconcerting because the whole theory was that the ether would form some kind of resistance against the east-west light beam, enough where they could show that the Earth was moving at 30 kilometers per second around the sun. What they got was probably about 1/10 of 30 kilometers per second. Let's say about 3 kilometers per second. Okay, and so he hired, Michelson consulted with Heinrich Lorentz, who was another famous physicist at that time. And he said, what's going wrong here? And so Lorentz said, well, maybe one of you have a mathematical miscalculation in one of your equations here. And that's why the figure came out to be, 1/10 of what we expected. And so Michelson said, okay, all right, maybe you're right. So he prepared to do the experiment again in 1887, and he got funding from the National Academy of Sciences in the United States, and also from Alexander Graham Bell.
And this was the Michelson-Morley experiment?
Yeah, this is the second one now. This is he took on a partner now, Edward Morley, and did the second interferometer experiment in 1887, 6 years after the first one. And basically it was to find out whether the first experiment was valid. Is this result that was totally unexpected in 1881 going to stand up? Okay, so what you do the experiment again. So they did the experiment again, and now they made it even more sophisticated. It was going to be able to measure these light beams a lot more accurately than the 1881 version. And so they did the experiment. They did it over 6 days. They had 36 trials, and it came out to be almost exactly the same result as occurred in 1881. And that is, they expected fringe shifts that were on the order of 30 kilometers per second of the Earth going around the Sun, and what they got was, between 3 and 8 kilometers per second. All right? So again, they were so disconcerted. What do you do with this? We've all believed that the Earth is revolving around the Sun, and yet these experiments are showing that it's not revolving around the Sun. Now, mind you, they can't have a result that's like 5 kilometers per second or 15 or 20. They have to have 30, because the Earth has to complete its orbit around the Sun at 30 kilometers per second to finish it in 365 days. Right?
Exactly.
You can't have it going any slower than that. All right.
Right.
So this was quite a dilemma. So they were scratching their heads for many, many years. Lorentz wrote to many people. He wrote to Oliver Lodge. He wrote to Lord Kelvin, Lord Rayleigh. These were all famous physicists in England at the time. And he said, what are we going to do about this experiment? And so he was, working at it, finally came up with this theory that the reason the interferometer did not measure any displacement of the wavelengths was because since the Earth was moving, the ether was compressing both the Earth and the arm of Michelson's apparatus. Okay? Mm-hmm. So in other words, we expected the length of the wave to be x, but it's x minus y because as things move through the ether, they are compressed. And so now the x is not minus y, it's x minus 0. And so you have x as your remainder, and therefore that explains why Michelson's interferometer could not detect that the Earth was moving. And that's because Michelson's interferometer was distorted. Okay? It was distorted as it moved. And they call this length contraction. In other words, if whatever direction you're moving, in the direction that you're moving, your body, or the object is shortened in the lengthwise direction. The width and the depth are okay, it's just the length is going to be distorted because it's moving. That's the best thing he could come up with to explain Michelson's experiment. And he had no scientific basis for this whatsoever. He did try to go into electron theory and say that the electrons would be compressed, and therefore that would compress the length of Michelson's apparatus, and blah, blah, blah. But it was all theory. And he even called it a theory. As a matter of fact, I think one of his papers in 1886 was an attempt at a theory to explain Michelson's experiment.
Wow.
Yeah, so,
So it's sketchy at best.
oh, yeah. I mean, science kind of works like this somehow. They come up with a theory and then a theory to explain the empirical evidence, and then they try to see if they can prove the theory, you see. And so science is by and large, it deals, precisely along those paths where you see the evidence, it's disconcerting, so you make a theory of why it's that way, but it's just a theory. There's no proof to it. And it just so happened that, there was another scientist named George Fitzgerald who had come up with the same idea that Lorentz had come up with right around the same time. And so they were exchanging notes. And Fitzgerald had written a letter to, Lorentz in 1894, and he said, "Oh, I'm so glad you came up with this theory, because I had come up with this theory and everybody's laughing at me over here in Dublin." He was a physicist in Ireland at the time. And I have the actual letter that he wrote to Lorentz, complaining about how he was being laughed at for promoting this contraction theory of electrons to explain Michelson's experiment. But that's the only thing they came up with. Either that, or they would have to admit that the Earth wasn't moving, you see. They had two choices. You either say that the apparatus is contracting, or the Earth isn't moving. Now, which one do you think they're more inclined to accept?
The incredible shrinking machine, as quoted from your book.
Incredible shrinking machine, yes, that's what I call it.
Mm-hmm.
So anyway, that was the start of, it's ironic because science, modern science, and let's say it started after the time of Newton, modern science believed that the more information they would find in the natural sciences, the more they would explain away the Bible, theology, and we could just depend on science, you see. But what they were finding was just the opposite. All the experiments that they were doing were actually bringing them closer to the Bible and the Bible's view of cosmology, that is, that the Earth is in the center and isn't moving, than all the centuries prior, when they did no science experiments, you see. So, science basically got undercut by its own, or what they say, hoist by its own petard.
Yeah.
That's what was happening.
Mm-hmm.
So, this is where they were stuck. Now, Einstein came along, in 1905 with his famous paper, the electrodynamics of moving bodies. Now there's the title, Moving Bodies, okay? The moving body in question here is the Earth, alright? So basically Einstein's trying to explain by this famous paper how the electrodynamics that are going on can explain why this moving body that we believe is moving wasn't detected as moving by Michelson's experiment, okay? Now, he was very familiar with, Lorentz's work. He was also familiar with the relativity theories promoted by Ernst Mach and Henri Poincaré, another French scientist. And so Einstein basically put all these things in a jar, shook them up, and came up with this special theory of relativity to explain Michelson's experiment. And basically what he did was he advanced beyond Lorentz's explanation of ether. And he said, well, look, you know what? You can make this very simple. If we just do away with the ether altogether, we can have an easier time explaining Michelson's experiment. And he knew that he had to do away with the ether because if the ether is out there, we should definitely be able to measure movement against that ether. See, it's not really hard because Michelson's experiment was so precise, it could have detected a difference in speed down to 1/100th of what he actually found. It was so powerful, a piece of machinery that he had built. And so Einstein knew instinctively that, the only way that you can get out from under this cloud that was created by Michelson's experiment was just to say that ether doesn't exist. But that wasn't all. He still had to explain in a different way why Michelson's apparatus did not detect movement. You see, because that's basically what special relativity says. It says we can't detect movement. We don't know whether we're standing still or moving at uniform speed because we're not going to feel any inertial forces at those two speeds, either still or moving uniformly. So, and that's what special relativity deals with. So he still had to explain Michelson's experiment, and he didn't want to use ether because that would trap him the same way Lorentz was trapped. And so he said, okay, let's do away with ether, and let's just say that as an object moves, it's moving relative to other things, and so the length contracts of the object and the time dilates for the time that it's traveling, just as a principle of nature. Okay?
Yeah.
There you go.
And go ahead.
No, you go ahead.
Yeah, I was going to say, I was listening to a documentary, a very short one by Malcolm Bowden. Are you familiar with this fella?
Yes, he's another old fellow. He's been around for a long time.
Yeah, and he talked about this, and he said that the paradox of the clocks proves that Einstein was wrong. Would you agree with that?
Yes, definitely. And this was an objection brought up by Herbert Dingle in the 1940s and 50s. Herbert Dingle was a very famous physicist, and he's got accolades, after his name that are very impressive, very well known. He was a original supporter of Einstein's relativity theory, and then he came up with the clock paradox.
Could you explain the clock paradox to the audience that might not be familiar?
Yeah. What it's saying is, you can use the twin paradox. That's probably what they're most familiar with.
Sure.
The twin paradox is, let's say you have two twins on Earth, and then one gets in a spaceship, we'll call him Twin B, and he goes away very fast on this spaceship, and then he comes back on this spaceship to Earth. Will he have the same age as Twin A? And special relativity says no. He will be younger. Twin B will be younger than Twin A because when Twin B got in the spaceship and he traveled at a certain speed, and that speed will dilate time. Now, I think this is a misnomer. They should not be using the word dilate, because dilate actually means to enlarge. What they actually mean is contract. The time will contract for Twin B, and it will be a different time calibration than it would be for Twin A, who's still on Earth. Okay, so if Twin A comes back, Twin B comes back to Twin A, and he's younger. Well, Dingle's objection was, well, wait a minute. Didn't you say that everything is relative in special relativity theory? So why are you saying that if Twin B goes away, that Twin A can't age at the same rate as B? Because the distance between Twin A and Twin B is all relative. Okay? The experiment is assuming that Twin A is standing still and Twin B is moving away from him, but you can't say that in relativity. Relativity says we can't tell the difference whether Twin B is moving away from Twin A or Twin A is moving away from Twin B.
Brilliant.
So how can you say that the time is changing for Twin B and not for Twin A?
That's right. You use relativity against itself.
Yeah. It eats itself up.
Yeah, it does.
And so that was Dingle's objection. Nobody ever answered him, but Einstein was so popular at that time, nobody was listening to Dingle and nobody wanted to listen. They had their answer from Einstein about how the world was running, and Einstein saved them from going back to the Middle Ages, where they believed the Earth was not moving, it was in the center of the universe, and that's all there was to it. So there's not much more somebody could say against Einstein, because he was basically the new Copernicus, so to speak. And he did save mankind from having to go back to the Middle Ages, because Michelson's experiment was empirical evidence that the Earth wasn't moving. And as a scientist, as I said before, you just can't walk away from this stuff and say, oh, well, that was just a mistake. No, it wasn't a mistake. I mean, Michelson did it twice and found almost the same result each time. Then he did it again in 1897. What he did was he took it out of the basement of Case Western University and put it up ground. Because there were complaints that, well, maybe the ether wasn't moving right in the basement or something, you know. So he moved it up above ground and got the same result. Okay, that was in 1897, 10 years later. Then he did it again with a guy named Miller in 1904. And then he did it again. Dayton Miller went on his own track and did it. He did 100,000 trials as compared to 36 done by Michelson Morley.
Okay, can you just repeat that number once again? 100,000 experiments?
100,000 trials, yeah.
And
he got the same
you got the same results with each.
In fact, he got a little higher ether drift than Michelson Morley. He got an average between 5 and 8 kilometers per second. Theirs was around 4 to 5 kilometers per second. And he wasn't the only one. There were dozens of these experiments done over the course of the next, 3 decades, up until 1932 with a guy named Joos, Joos. They all found the same thing. They all found that they could not, use interferometers to detect the Earth moving, but they would always get this residual effect. They would always get something, okay? 1, 2, 3, 4, 5 kilometers per second, so this was bothering them too. If the Earth isn't moving, well then why are we having this little residual here? This little reaction. And I'll explain that later. But the fact is they could not show the Earth moving through, space at 30 kilometers per second. And, so Einstein was basically a savior for them. He cooked up this special relativity theory to answer Michelson. And basically what he said was the reason Michelson's apparatus couldn't detect the Earth moving was because the arm of his apparatus shrunk just enough so that we could not see the Earth moving. Just enough. Okay? And time now this is the dilemma that they're in. If you're going to say that the object is shrinking, well, how much time is it going to take for that object to pass from point A to point B? That's interesting. If it's shortened, that means it's not going to reach the finish line at the same time, is it?
That's right.
Okay, so that means then we have to change the time as well. Because that object has to pass from point A to point B in the same time as if it wasn't moving. And if we can't explain that, then we need to create another fudge factor, and that's called time dilation. Okay? So we change the time that this object moves so we can account for the fact that all of its mass goes past point B in the required time. Well, what does that do? Well, that means if you have an object that's compressing, let's say you have a putty, and you compress the putty down from from a big ball to a little ball. What have you done? Well, you've changed the density of that putty, right? A putty ball. All right. So if you contract an object, you're changing the density of that object, basically, because its dimensions are now different, but it has the same mass. Mm-hmm. So that its mass has to increase. Okay? Mm-hmm. Well, that's exactly what special relativity predicts also. The time is shrunk, the length is shrunk, but the mass increases. Okay? And all they do is basically invert the equation, from, 1 over 1 minus, v squared over c squared, and invert it so that now it can divide and get more mass for the object. It's all, it's a lot of, trickery with math that they use on these things. And the ironic thing about this is that, Lorentz, the guy that believed in ether and that Michelson's apparatus was shrinking because it was rubbing up against the ether as the Earth went around the sun, well, he came up with a formula called the Lorentz transform. Okay, and the Lorentz transform is basically an equation that will always make the ratio less than 1. And that is, if the ratio is less than 1, that means the object is smaller than it was when it was standing still. 1 would be when the object is standing still, and 1 minus would be when the object is moving. And Lorentz put that into an equation called the Lorentz transform, and that equation is probably the most famous equation in physics today. Every physics experiment that deals with objects in motion will incorporate the Lorentz transform in their calculation of how that object is moving. The whole theory of relativity from Einstein, whether it's special or general relativity that was invented later, all are based on this equation that Lorentz formulated in order to answer Michelson's experiment. And you can go on the internet and find it. Look up Lorentz transform, and you'll see an equation that says something like this. L prime equals L times the square root of 1 minus v squared over c squared. Okay? And the reason he put it in those parameters was because that would make the length always less than the original length if that thing was standing still. And that's what they needed. And Einstein commandeered this formula from Lorentz, except he didn't use ether. Yeah, that's the difference between Lorentz and Einstein is Lorentz at least had a physical basis for why he said these things were shrinking and time was shrinking, because they were rubbing up against ether. Einstein got rid of the ether and just said, well, when things move, it's just a principle of nature. They shrink and time contracts. And nobody asked any more questions after that. You see.
Just accept it.
Just accept it, because it was Albert Einstein. And
so the mental gymnastics that Einstein had to perform to get rid of this experiment are extraordinary.
Extraordinary, yeah. Yeah, it's like a haunted house of mirrors. Nothing is as it appears to be. Lengths are shortened, time is distorted, and mass increases. You ever walk in front of one of those mirrors at a amusement park?
I have indeed.
And it's wavy and you see your body all distorted? Mm-hmm. Well, that's pretty much what special relativity did to science. It was a total revamping of physical science. That's why it was so important, okay? And that's why it's a revolution in science.
I heard that some of the best scientists in the world that were first exposed to Einstein's relativity walked out after he was finished. Is that so?
Oh yeah, there were a lot of people that didn't accept. I have a whole list of them. There's probably about 50 names of famous scientists who rejected special relativity. Albert Michelson was one of them. Never accepted it till the day of his death. And Dayton Miller never accepted it. He's the other guy I told you about. Mm-hmm. Even Max, is it Planck? Yeah, Planck, I forget which, Max Planck didn't like either special or general relativity, one or the other. But yeah, he had a lot of enemies. Mm. This was a theory that, it couldn't be proved. Okay? Some will come along and say, yeah, well, we can prove that mass increases, in a cyclotron, they're not proving that mass increases in a cyclotron. So in fact, this was one of the arguments that Dingle had brought up, that, you can't say that because that's not what's going on in the process. And even from an ether-based, scientific foundation, you can say that the reason that electron appears to gain mass is because it's running through the ether. There's an ether pressure there. So it's going to look like that the electron has more mass. So, even the supposed proofs that they have that, special relativity is true are not proofs at all. It's just the way they interpret things. But people need to know, and that's the education we want to give them now, is the birth of special relativity, Einstein's relativity, was not because it was some, I don't know what you would call it, a theory that just, grabbed everybody's intellects and just, was so persuasive that we just couldn't avoid it. That was not the case at all. Special relativity was invented for one reason and one reason only, and that was to explain away Michelson-Morley's experiment that showed the Earth wasn't moving. That's why it was created. Okay? So, people need to know that. That's the basis of it. And the whole, you can understand the whole thing too, because if you have, it's called a special theory of relativity. Well, what does relativity mean? Relativity means there is no non-moving object. There is no Earth that is not moving. Otherwise, nothing would be relative, would it? You see, if everything is moving, then it is all relative. So a non-moving Earth is the total antithesis of special relativity. We have two different worlds here now. Okay,
there would be no constant.
No constant, yeah.
Yeah.
And even in astronomy today, if the Earth were motionless, you could use triangulation to figure out, where star B is as opposed to star A, because you have a fixed point from which to measure from, and that is the Earth, the non-moving Earth, you see. So, but there was a lot at stake here. I mean, think about it. If Einstein couldn't come up with a theory to counter Michelson's experimental evidence, then what was going to happen? Well, we would all be worshiping at the feet of the Catholic Church, because who was the one who decided back in the 1600s that when it was proposed to them that the Earth was moving, they condemned it as heretical? Well, that was the Catholic Church. Okay, so there's a lot at stake here.
And that was a de fide declaration, correct?
No, it was not de fide.
It wasn't? Okay.
Yeah, it wasn't a de fide ex cathedra statement from the Pope. But that's an argument that's lame, because, there are maybe about 3 instances in the whole 2,000 years of Christendom where the Pope actually said something ex cathedra. Mm-hmm. Okay? And the Church has never given us a list of ex cathedra statements for anybody to contest that. Mm-hmm. So that's really not an issue. Well, what is an issue is the fact that the whole tradition of Catholicism, beginning from the Church Fathers through the medievals, through the Tridentine Catechism that was published in 1556, and then the two popes
that's the Catechism of the Council of Trent?
Yes.
Mm-hmm. Okay.
And then and the reason I mention that is because it supports geocentrism in 4 different places. Mm-hmm. Not too many people know that. And this is all put in our book, as a matter of fact, for people to go and explore it. And then you had 2 popes who, though they did not speak ex cathedra, they, by their vested authority as the Pope, approved the condemnations issued by the Holy Office against Galileo and heliocentrism, to the point where in 1633 they said that heliocentrism was a formal heresy. And that was a statement from the Holy Office, and it was approved by Pope Urban VIII. Not only was it approved by him, but afterwards he sent letters to all the papal nuncios in Europe and all the universities telling them what the Church's decision was against Galileo, and that they had declared heliocentrism a formal heresy. Okay? So this was no pansy pope. This was no guy who was just sitting by the sidelines, waiting for things to happen. This was a pope who was intimately involved with this process. As a matter of fact, prior to Galileo's trial in 1633, he had protracted discussions with the Duke of Tuscany, Cosimo Medici, and told him that he needed his help to silence Galileo because Galileo was preaching heresy. This was all occurring in 1630, 1631, and then in 1632, Pope Urban called Galileo back from Florence, and he found out that Galileo had surreptitiously got an imprimatur for his book, the Dialogo, which was promoting heliocentrism, and he rescinded it right in 1632.
Now, can I just interrupt you for one moment there? That was an imprimatur. That was not a nihil obstat, correct?
Well, you would get a nihil obstat before your imprimatur. I think that was a process even at that time.
Okay.
But he got it surreptitiously, and what I meant by that was that he got Father Riccardi more or less cornered by some high-placed cardinals, and more or less pressured him into giving him the imprimatur. And they used some subterfuge because Riccardi was supposed to approve page by page before he gave the imprimatur, and somehow they got Riccardi to renege on that, and so, they just didn't follow proper protocol. Let's just put it that way, when they gave him the imprimatur. And that's all water under the bridge for the fact that it was taken away from him anyway in 1632. So, that's what Einstein and his fellow colleagues would have had to come under if they couldn't show by at least some scientific abracadabra that the Earth, wasn't moving. And so, this Michelson Morley experiment was a real thorn in the side. And it took basically from the time Michelson did his first experiment in 1881 until Einstein came up with a special theory of relativity to explain it away, 25 years, a quarter of a century of these men scratching their heads saying, how are we going to answer this experiment? What are we going to do? And then they had all these other experiments prior to Michelson Morley. They had Arago that I already explained. They had Airy, that was giving them difficulty when they looked at starlight. Okay? Now they were back in the laboratory with Michelson Morley, and they were still, things didn't improve. They got worse when they got into the laboratory.
Yeah.
So,
their expected results never manifested.
Never manifested.
No.
And that was true until 1932 when Jews did the last, interferometer experiment. He didn't come anywhere close to what they needed. And then in the 1950s and 60s, they started to use lasers and masers.
Doctor, before you get there, just one moment, if you could. We're in the 20th century now. Could you talk about Sagnac? I thought that guy was incredible. And 1913?
Yeah, it is incredible. Thanks for bringing that up.
Mm-hmm.
Sagnac, S-A-G-N-A-C, another French scientist. It's amazing how many French scientists were all involved in this.
It is incredible, isn't it? My God.
Yeah, I went to Paris. I went to Paris a couple of years ago, and I was standing underneath the Eiffel Tower, and there you could see all their names. Fresnel, Fizeau, Arago, are all up there on the Eiffel Tower. It was and I could see that the French would be very proud of that, because scientists were, the best scientists in the world at that time. Anyway, Sagnac, did a, experiment in 1913, and, it was very similar to Michelson Morley's experiment.
Doctor, just before you talk about that, you want to take a break? We've been talking here for about an hour and 20 minutes. You want to take a few minutes break to just catch your breath? Or you just want to forge ahead? It's up to you.
Yeah, I'm gonna get a drink of water.
Okay, folks, we're gonna take a little break here. I'm gonna play some of the Planets by Gustav Holst while you wait, okay? And we'll be back with Dr. Robert Sungenis on geocentrism in a few moments. Okay, folks, we're back. You're listening to Media Streaming International. I'm Live Mike, and I'm joined by, arguably the greatest guest I've ever had, Dr. Robert Sungenis, here to talk about geocentrism. Doctor, before we went to break, we were talking about the Sagnac experiment of 1913. Would you like to talk about that, please?
Yeah, this is the second leg of the Michelson-Morley era that was started in 1887. And the connection is this. Sagnac did his experiment in 1913, and it was the same kind of interferometer machine that Michelson-Morley had used in 1887, except that instead of having the light beams go back and forth perpendicular to each other, he had them go around a circular set of mirrors, and he would rotate this frame the same way Michelson-Morley rotated their frame for the perpendicular beams. The purpose of the Sagnac experiment was to show rotation as opposed to revolution. In other words, they wanted to Sagnac wanted to show through the rotation that he detected that there was absolute motion between the Earth and space. Whereas, Michelson-Morley specifically wanted to show that the Earth was revolving around the Sun. And that might sound a little complicated. I'm going to try to make it simpler. Sagnac basically wanted to see if he could find a 23-hour, 56-minute rotation of the Earth on its axis. Okay? And this is very important because in 1925, the same Albert Michelson that did the Michelson-Morley experiment in 1887 teamed up with another person, Henry Gale, in 1925, and he did a very similar experiment to Sagnac's 1913 experiment for the express purpose of determining whether he could detect a rotation, this would not be a solar rotation, this would be a sidereal rotation of 23 hours, 56 minutes of the Earth on its axis. Okay? So, what Sagnac found was that yes, there was a rotation. 23 hours, 56 minutes. And Michelson-Gale found the same thing. Almost 98%, their interferometer was so precise that they could get within to 98% of a sidereal rotation between the Earth and space at 23 hours and 56 minutes. This was remarkable because when Michelson did his experiment in 1887 with Morley, he couldn't even come close to a fraction of what he needed for the Earth's revolution around the Sun. And yet he was getting in 1925, along with Sagnac in 1913, close to 98% of a 23-hour, 56-minute diurnal rotation of the Earth. So that this was interesting. How do you explain that if you're a heliocentrist, how do you explain that the Earth has no revolution? That is the same interferometers, you're working by the same exact principles, just 30 years apart, can't detect the Earth revolving around the Sun, but they can detect a daily rotation. How do you explain that if you're a heliocentrist? Well, you're going to have a hard time. Because in heliocentrism, you have to have both a revolution of the Earth around the Sun and a rotation of the Earth on its axis in order to account for the day-night rhythm and the four seasons. If you don't have both, then heliocentrism is falsified. You have to have both. You can't have a revolution without a rotation, and you can't have a rotation without a revolution. Otherwise, heliocentrism is falsified. Okay? So that's a big problem. And that's why, as you might guess, no one talks about the Michelson-Gale experiment of 1925. And not too many people talk about Sagnac's experiment in 1913, or at least they don't talk about the full implications of that experiment. They do talk about this thing called the Sagnac effect, but then they distort that so that nobody can see behind it. And I'll give you a good example how that takes place. Sagnac found that there was a sidereal rotation. He found that there was absolute motion between the Earth and space. Okay? So what does modern science do with that? Well, they don't exactly know what to do with it. They just call it the Sagnac effect and leave it sort of unexplained. But then when you get to issues like the global positioning satellites,
yeah,
wow.
This is fascinating stuff. As soon as you bring up GPS and you look at what NASA does with these old experiments and how they, I don't want to spoil it. Go ahead, Doctor.
Well, I was waiting for you to explain it. If you want to go ahead.
No. I'd rather listen to the expert. I don't want to hear me.
All right. Well, and it's funny how we found this out. In making our movie, we contacted one of the people who works. He works for NAVCOM in California, and he is under employment for John Deere. Now, John Deere, as you know, makes all kinds of tractors and things of that nature. And they have this tractor, this new tractor that works all by itself, basically. You don't have to have someone drive it. And the reason you don't is because it's guided by the GPS, the global positioning satellites. Okay? But in order to get to the point where you don't need a driver for one of those tractors to plow those fields, well, you got to know that GPS system backwards and forwards, because there's some, intricacies there that if you don't make the proper adjustments, well, that tractor's going to go off into the ditch. Okay? So they have to make sure they know how that GPS works. And this guy who was in our movie, Ronald Hatch is his name. You can look him up on the internet. He had to go and investigate line by line how they were constructing the computer data, or computer programs rather, for the positioning satellites. What he found was that they, without telling people, pre-programmed the computers of the global positioning satellites to include the Sagnac effect. Now, this is the same guy we're talking about who did his experiment in 1913. He found, by his experiment, absolute rotation. Okay? In other words, he found absolute motion. And what does that mean? Well, if motion is absolute, that means it's not relative. If you can prove that motion is absolute by your experiment, that is a phenomenal experiment. And they can't get away from it, because what they have to do now is they have to pre-program their computers for this Sagnac effect of absolute motion without telling anybody. And then they say that the global positioning satellites are working by the special theory of relativity. That's what you'll find today. You go look on the internet. Yeah, well, the global positioning satellites prove the special theory of relativity. No, they disprove the special theory of relativity, because if those computer programs of the GPS were not pre-programmed with the Sagnac effect, and in other words, if they weren't adjusted for the fact that there was absolute motion, then the GPS wouldn't work. They'd be off every time, and that tractor would fall into the ditch because it wouldn't be guided correctly unless it was adjusted by the Sagnac effect. Now, what they have found between GPS satellites in space, like they work in foursomes. They have three up in space and at any one time, and they have a ground station. And what they found was when a signal is sent from one GPS in orbit to another GPS in orbit to get the triangulation that they need, well, they found out that the light beam rather, that goes from west to east travels 50 nanoseconds slower than the light beam traveling from east to west. 50 nanoseconds. Now that may not seem like a lot to you, but if you add up 50 nanoseconds for every beam that's sent from one satellite to the other, and you add that up for a day, well, that would mean the typical GPS would be off by 15 miles. Okay?
Sure. They
have a certain parameter that they have to fit into, and so they have to measure these things in nanoseconds, and that's a pretty intricate calculation. But that's what they discovered. Okay, now why is that the case? If light always travels at c, as Einstein told us, okay, then why are these GPS beams coming back at different times? 50 nanoseconds worth. Okay, therefore you've just falsified the special theory of relativity. In other words, the global positioning satellites are just one big Michelson-Morley experiment. It's 1887, or it's one big Sagnac experiment. Okay, the only way that they can adjust it to prop up special relativity is by adjusting the computers based on what Sagnac found in 1913. Okay, so there's a story for you. That should make headlines, but you won't find it in the headlines, of course. All right, because the aura around special and general relativity is so great, not only to answer Michelson-Morley, but is the absolute foundational basis for all of cosmology today. Everything you hear about the Big Bang and the expansion and dark matter and dark energy and inflation and all these terms you hear are for one reason only, because everything has to be fit into the tensor equations of Albert Einstein, G equals 8 pi t. Okay, that's the reason why. So, and that all comes from general relativity, which is the next step that we want to talk about. Special relativity was invented in 1905 to answer Michelson Morley, to keep the Earth moving around the sun. And then we began to see flaws in special relativity, and one of the major flaws, of course, is that it doesn't deal with gravity. If you remember at the beginning of the program, I said that special relativity dealt with uniform motion, and that is motion that's going the same speed all the time, or you're standing still. Okay, that's called an inertial frame. Now, what happens when you're accelerating, however? Or what happens when you're decelerating? What happens when you meet up with inertial forces like centrifugal force or Coriolis force or Euler force? Well, things change, you see. Now you have to have a whole new theory, and that's why Einstein had to develop the general theory of relativity, because he had to answer gravity and inertial forces. Where do these things come from? Well, general relativity proposes to give us an answer, and it says space is warped and time is warped by matter and all kinds of things like that. These are totally unproven too, but that's just the theory. Okay, that's why it's still called the theory of general relativity, because none of this has been proven. And anybody who says that general relativity has been proven by, the bending of light waves around the sun that Eddington found in 1919, that's all unproven as well. And I've written extensively on that in my books. If anybody says that relativity has been proven by the perihelion of Mercury that Einstein found, as opposed to Newton not finding it, that's all hogwash too. There has been no proof for general relativity. There are things that have been propped up as truths of general relativity, but no substantial proof based on the data that's been given to us. Not many people know this. Not many people will know it, but I'm telling you, and so do your own investigation. But anyway, general relativity was invented by Einstein to supplement special relativity, and he incorporated gravity and inertial forces. But by doing that, what he did was something that he never expected. And that is this. In general relativity, there really is no difference between an Earth rotating in a fixed universe as opposed to a fixed Earth with the universe rotating around it. Why? Well, because it's relative. Everything's relative, you see. So if it's going to be general relativity, well, general relativity must allow both systems to be viable. And this is why in 1938, when he wrote his book with Infeld called The Evolution of Physics, Einstein admitted that, well, there really is no difference, relatively speaking, between the Earth going around the Sun and the Sun going around the Earth. We have no power in general relativity to distinguish one from the other, because everything's relative, you see. So, and then you have developments of relativity by Max Born, by Barber and Bertotti. All kinds of people were doing mathematical equations to enhance general relativity, and they were all finding the same thing. What was it? Well, they were all finding that if you have a fixed Earth and a universe rotating around it, that universe and its movement is going to create the same inertial forces that you feel on Earth if you have the Earth rotating under a fixed universe. In other words, let's look at it this way. If you have a universe rotating around a fixed Earth, you're going to have the same centrifugal forces that cause you to fall off a carousel if it's going around too fast, or it's going to cause the same centrifugal force if you have a rock on the end of a string and you whirl it around your head. Well, that's going to be the same inertial forces that are created in a rotating universe around a fixed Earth, as if and they're going to be equivalent to an Earth rotating inside a fixed universe. These are things that Einstein wrote about from his theory of general relativity, and he used special terms, but they basically said the same thing. And so it's ironic when you look back on the whole history of this with Einstein that he invented special relativity in order to keep the Earth moving, in answer to Michelson Morley's 1887 experiment, which then led him inevitably to have to invent general relativity. And when he invented general relativity, he made geocentrism viable because now he had to admit that there is no difference between an Earth rotating in a fixed universe as opposed to an Earth fixed in a rotating universe. So it's ironic that the whole trek through the relativity theory that was started off to deny geocentrism ends up actually supporting geocentrism better than any theory we could concoct ourselves.
Doctor, I wanted to ask you about the star field that travels around the Earth as the center. Now, this has to be traveling at an unbelievable amount of speed for every star to complete that rotation in a 24-hour period of time, yes?
Yes and no.
Okay.
We need to explain that.
Okay.
All right. Let's look at it from the general relativistic viewpoint first. All right. If general relativity says that is, and by this, I'm not saying that I agree with general relativity at all. All right. I'm just using their own scientific foundations to help them understand why a geocentric universe is viable from their own terminology. Okay. From their own scientific foundations. General relativity says, and not many people know this, and not even many physicists know the implications of this, but general relativity says that the stars, the star field, if you want to call it the star field, can travel at any speed. It can travel at any speed above the speed of light. Okay? Because general relativity is based on inertial forces. And it says that the greater the inertial forces, and so the typical inertial force here would be centrifugal force. The greater the centrifugal force, the faster an object, or the faster light can travel in the universe. And so it's not limited to 186,000 miles per second. All right? Now that's interesting. Let's go back a little bit. Special relativity said that the speed of light was constant at 186,000 miles per second. Does general relativity say that? No. It says just the opposite. It says that light can travel at any speed. And that speed will be determined by the inertial forces that it encounters in its travels. The higher the inertial force, the faster light's going to travel, in the theory of general relativity. So you have a major contradiction between special relativity and general relativity. The speed of light is not constant in general relativity, and general relativity is the theory that encompasses most of the universe, according to Einstein. Not special relativity. Special relativity is a special case because it's in the absence of mass and gravity. Okay, well, we don't have any quadrants in the universe that are absence of mass and gravity, do we? No.
All right.
So it's general theory of relativity that's the predominant theory, all right? And that says that light can travel at any speed. It also says that any object can travel at any speed if it's in that centrifugal inertial force, you see. And you can find this written by relativists in their textbooks. I quote them all in my book. So, according to general relativity, no, it would not be impossible for the stars to travel beyond the speed of light.
And this has been proven, hasn't it, Doctor? Didn't they fire neutrinos or something like that, and they calculated the time and they saw that it exceeded the speed of light?
Well, that really has nothing to do with what we're talking about
Okay,
here.
I'm sorry.
And that really has not been proven that neutrinos could travel there. That's another subject altogether.
Okay.
They did have the dog-ate-it excuse when they tried to give an example of it and said, one of the cables was loose. But, whether that's an acceptable solution, if that's the case, well, let's go back and do the experiment again, just dealing with neutrinos. But that has nothing to do with what we're talking about here. We're talking about mathematical equations that determine gravity and inertial forces in a rotating reference frame. That's what we're talking about here.
Okay.
And so that's a very different topic. And basically the only reason I'm going into this is to show the relativists out there or the people that are anti-geocentrism because, well, the stars can't travel that fast around. Oh, yes, they can. Oh, yes, they can. According to general relativity's mathematics, they can. You see, there is no difference between a fixed Earth and a rotating universe and a rotating universe within a fixed universe in terms of general relativity. And if that's the case, well, then the stars must be able to travel that fast in general relativity. And I show all the mathematical equations in my books, all the quotes from Einstein and Mach and Born and Bertotti and all these guys who have dealt with this stuff. There's many more of them too. Brown, Nightingale, you name it. They've all dealt with this stuff, and they've all shown that general relativity's equations will allow the universe to rotate around an Earth. Now, if we deal with it in a non-relativistic framework, a geocentric framework, how do we explain it? Well, very easily. The stars are not the things that are moving at tremendous speeds. The stars in the geocentric universe are embedded in the ether. And that ether is in the Planck dimensions. Okay? We can't see it, we can't feel it, it's there, and that's the composition of the universe. Now, you can have a Planck dimension universe rotate 1 trillion times faster than the universe is presently rotating on the sidereal rate, and it would not fall apart, because the Planck universe in Planck dimensions is so stable because of its granularity and its mass and its temperature that it would never fall apart. So from a geocentric framework, we have no problems showing how the universe can rotate and still be intact. As a matter of fact, a rotating universe answers the perennial problem that the Big Bang theorists have had since its inception. When the Big Bang was invented by Lemaitre in the 1930s, the first question that popped up is, well, if we had a Big Bang, and that was opposed to the infinite universe of the steady state system, if we have a Big Bang that had a beginning and it exploded, well, how is it going to be that that explosion is going to not slow down and not start contracting until it contracts to the big ball from which it started, or the little ball from which it started, 13.7 billion years ago. Okay, how do we explain that? And here's their dilemma. Their dilemma is, if we have a infinite universe, infinite in mass and in time, and that's what Einstein had believed originally, until he saw the redshifts of Hubble's galaxies, okay? They were comfortable with an infinite universe because they didn't have to account for a beginning and an end, okay? But now Hubble comes along and he says, look, I'm seeing these redshifts in these galaxies. That means there's movement out there in the universe, and they're all moving away from us. And if they moved away from us, well, that means at one point in time they all had to be together. You see? You can't have movement away unless you had movement from. And so the movement from was then designated the Big Bang. All right? Well, if you have a Big Bang and you have this explosion occur and all this matter is going away, well, eventually it's going to have to come back together again into this point from which it started. And this is the very reason that Newton wanted an infinite universe after he formulated his equations of gravity. Because he figured out, he said, well, if F equals ma and F equals g m1 over, his gravitational equation, which was F equals gravitational constant times mass 1 times mass 2 over r squared. Well, if that's the case, then all this matter is going to come back and congeal again into one big solid ball. So I need to make the universe infinite so that it doesn't come back together in this big ball. That's why he believed in an infinite universe. And so did Einstein until he saw Hubble's galaxies. So now you have this Big Bang that they have to account for, and they can't account for it because they can't figure out how to keep the universe from coming back together in this big ball under the gravitational formulas of Einstein's tensor equations. Okay? So what Einstein tried to do was he put in a fudge factor called the lambda factor to keep the universe stable, the same stability that it had in the infinite universe. Okay? And that they've been trying for the last 70 years to come up with an equation and it's coming up with an equation to keep the universe in balance where it doesn't expand too much and it doesn't contract is like balancing a pencil on its point. They can't find the equation. And some men have given their whole lives to try to find this equation. How can we balance out gravity with the energy that is being used to expand the universe? They can't find it. Okay? And if they can't find it, that means the whole Big Bang Theory is falsified. Why? Well, because you can't, if you believe the universe is infinite, and yet it blew up and then it's going to destroy itself by coming back into this big ball, well, that could happen in a short amount of time compared to infinity, can't it? You see? So they're really trapped. They've painted themselves into a corner with this Big Bang Theory, and there's no way out. And the only way out they have today, that they've invented just recently, is called the multiverse. Have you ever heard of the multiverse?
I have, yeah.
Well, the multiverse is a theory that says, well, here's how we get out of this problem of infinity that we got when we invented the Big Bang. We realized that if we have this explosion, that explosion is going to retard itself and come back into this big ball. So how do we explain that? Well, here's the way we do that. We say that the Big Bang is just a product of another universe, another mother universe out there, you see. So, in other words, this mother universe had her little babies, and our Big Bang was one of those little babies. And then it exploded itself and created the universe we have today, you see. So in other words, what they've done is basically reformulated the infinity of Newton, and now they say that infinity is composed of a multitude of universes, that one universe creates another universe, you see, and ad infinitum. And you can go back and back and back and back.
And they have scientific proof for all this too, don't they, Doctor?
No, there's not a shred of scientific proof for this. Now, there will be some people, and I've read their papers, that are bold enough to say, oh yeah, we got scientific proof for a multiverse, you know, because they say, you see, there's dark matter stuff, and we see this dark matter between, their universe and our universe. And they say, well, dark matter, what are you talking about? Who discovered dark matter? Oh, well, we didn't discover dark matter. We just theorized that it must exist in order to have the galaxies rotate the way they're supposed to rotate, because without dark matter, they're rotating 10 times faster than they should. And we also need dark matter to expand the universe at the rate the supernovas had shown us back in 1998, you see. So, we have to have this dark matter. And if we have dark matter, then dark matter can lie between two universes, you see. And so, yeah, it just becomes silly after a while because it's all stuff made up from their head. Now, why are they doing this? Well, because the other side of the issue is the geocentric universe, you see. The geocentric universe doesn't have to have an expansion, and it doesn't have to have a contraction. It can exist with a rotating universe, and why is that? Well, all the gravity that's generated by the mass of the universe, okay, that would naturally congeal into a big ball in, a few 1,000 years or so. Well, that's all compensated for the fact that there's a centrifugal force created by a rotating universe that keeps all that matter away from every other piece of matter.
Is that the force that pulls upon the Earth to cause the bulge?
Yes, exactly.
Okay.
And that brings up a good point because, even a guy like Arthur Eddington, who had said he had found proof for general relativity in 1919 with the eclipse information, he's the one that said, well, quite frankly, the bulge of the Earth can be created if the Earth is rotating in a fixed universe or if the universe is rotating around a fixed Earth. He admitted it, you see. That's where the bulge can come from. And why is that? Well, because in both systems, the geocentric and the acentric or heliocentric, whatever you want to call it, will create the same inertial forces, you see. As a matter of fact, the Foucault pendulum, like you see in all the museums of the world today.
You see it in the Ben Franklin Institute. There's a giant pendulum there.
Yeah, I went there when I was a kid.
Yeah.
I was fascinated by Ben Franklin Institute. I saw the Foucault pendulum, and you'll see a sign there before you go see the pendulum, and it says, Foucault pendulum, invented by Jean Foucault in 1850. It shows us that the Earth is rotating underneath the pendulum bob that is oscillating. There's something to that effect. You'll see that. And, people by the droves go in there and see this and they, oh yeah, there's proof the Earth is rotating. It's no proof the Earth is rotating whatsoever. Why is that? Well, go back to this general relativity theory that Einstein created for all the populace. Well, that theory says that Foucault pendulum is going to change its plane of oscillation if the universe is rotating around a fixed Earth, just as if the Earth was rotating under a fixed universe. Both systems will work, you see. So that is no proof at all for the rotation of the Earth. Now this brings up the Michelson-Gale experiment again. Remember, that was the experiment done in 1925 by Michelson himself with Henry Gale, and he found a sidereal rotation between the Earth and space at exactly 23 hours, 56 minutes, and 4 seconds. Well, how could that be? Because Michelson didn't find a revolution of the Earth back in 1887, but he found a rotation. Well, the geocentrist comes in and says, well, here's the perfect answer. In the geocentric universe, it's the universe that's rotating around the fixed Earth in 23 hours, 56 minutes, and 4 seconds. And that's exactly what Michelson found in his 1925 experiments. How about that? And the geocentric system says, but there is no revolution of the Earth around the Sun. And isn't that exactly what Michelson Morley found in 1887? Yeah. They found that the Earth is not revolving around the Sun. But they did find that there was a rotation. Now, again, if you're a heliocentrist, you cannot have a revolution of the Earth without a rotation of the Earth. You have to have both. You cannot have one without the other. The geocentrist does not have those strict parameters. All he needs is a relative rotation of 23 hours, 56 minutes, and 4 seconds, and that's exactly what he got with the Michelson-Gale experiment, you see. So this should have falsified heliocentrism, but as I said, you won't find anybody talking about the Michelson-Gale experiment in 1920. Go try to look that up in a few textbooks in college or the universities or even from the Association of Physics in Europe or the United States. You won't be able to find anybody talking about Michelson-Gale. You will find a little bit on the internet, but they obfuscate it to the point where you can't understand what they're talking about, and they don't give any ramifications of this for supporting the geocentric universe. So, that's what we're up against today.
Doc, you said something in one of your presentations that I thought was awesome. I don't mean to be going backwards, but I just want to review if I could. You talked about the center of mass in relationship to what Newton actually said. Could you expound upon that?
Yes, thanks for bringing that up, because that's a very important point. Usually when, and this goes back to Galileo, as a matter of fact, because when Galileo looked through his telescope at the planet Jupiter, he saw 4 moons going around Jupiter. And he figured that since these moons were smaller than Jupiter, that the same principle of the smaller going around the larger would apply to the Earth and the Sun. We already knew from the Greeks that far back that the Sun was larger than the Earth. Nobody knew exactly whether it had more mass than the Earth, so there was a question mark there, but it was larger, so we all assumed it had more mass than the Earth. And Galileo and his contemporaries figured, well, if the smaller moons are going around Jupiter, then the smaller Earth should be going around the larger Sun. And this is a major objection that people bring up for geocentrism. How could geocentrism possibly be right? Because we know from modern science that the Earth is 1/1,000,000th the size of the Sun. So how could the Sun be going around the Earth? And, I'd say, yeah, that's a good question. As a matter of fact, why did Einstein say that in his 1938 book? Why did he say that there's really no difference between the Earth going around the Sun and the Sun going around the Earth? How could he say that? Okay. Well, here's why he could say that. Einstein, as I said, in his general relativity, already said that the same inertial forces would be created in either system. So they're equivalent dynamically. All right. Now let's look at it from a Newtonian perspective. Okay. Newton didn't really understand the stars. He didn't know how many there were, what kind of mass they had, and how they were situated in the universe. All he knew is that they were out there, and that's about it. What he did was he formulated his equations of motion and his gravitational equation on a closed system. That is, the closed system of the Earth and the Sun, or Mars and the Sun, or whatever. And in that system, if you have a closed system that does not include the rest of the universe, and you apply Newton's laws, 3 laws of motion, to the sun and the earth, well, the result would be that the earth would have to revolve around the sun. No question about it. Okay? That's because F equals ma, and if that is true, well then, the mass of the earth as opposed to the mass of the sun, that force equation has to be balanced, and the only way you can do that is by accelerating the earth, and that comes under the A of F equals ma. And it has to accelerate at a certain pace, otherwise it's going to be either sucked in or blown out, one or the other. So that's true. Now, what Newton didn't incorporate, however, was what Ernst Mach incorporated almost 200 years after Newton. Ernst Mach was a physicist, very astute physicist, and he had a lot of influence on Albert Einstein, as a matter of fact. And Mach's principle says this, that the absolute space of Newton was a fallacy, that his F equals ma applies, yes, to a closed system, but when you expand that system to include the rest of the universe, well, that's where the difference is. Because what Newton didn't do is include the force from the stars, you see. There's 5 sextillion stars out there in the universe. Some are much bigger than the sun, some are about equal size of the sun, and some are a little smaller. And when you add 5 sextillion stars out there, how much mass is that, and how much gravity does that create? Well, and especially if you consider that that stellar field of 5 sextillion stars is going around this fixed Earth. What will the mathematical equations be then? Well, we figured it out. We have shown, and I have had physicists work on this, they have shown that the Lagrangian points of a point particle in a rotating universe compared to a fixed Earth will allow the center of mass for the universe to be at one fixed point. And that point can be occupied by the Earth. And all the equations work. All Newton's equations work now if you include the stars in the gravitational mass with the sun and the Earth. And in layman's terms, what it would turn out to be is this. The reason the sun can stay 93 million miles away from the Earth, which is the center of mass of the universe, is because the stars are so fixated or so positioned in the universe that they counteract the force of the sun. They counteract its gravity and hold it in place, so to speak, as they rotate around the center of mass, which is the Earth. In other words, everything is all balanced by the same laws of Newton's motions as applied to a closed system. If we open that system up, all the same laws apply, and we can have the Earth now as the center of mass for the rotating universe, and the sun in the exact position it needs to be, 93 million miles away, because it's balanced between the center of mass and the stellar mass that's out there in the universe.
Doctor, there's a lot, this audience that we have here on MSI Radio is pretty educated, and some of them have written in the chat, and I just say this, I think I can answer this question, but there's a fellow that we have here that's concerned with referencing, even talking about Einstein, as he fears that we're reiterating the misinformation of Einstein. Now, I can answer this one and just simply say, you're doing it for the purpose of explaining what Einstein's thought is so that you can refute it, yes?
Yes.
Yeah.
I mean, there's nothing like using your opponent's bat against him.
Precisely.
Yeah.
Yeah, okay. There was also another comment, and this fellow, he says this, and I'll just read it verbatim, okay? And this has to do with the rotation of the Earth. The rotation, not the revolution around the sun, but the rotation of the Earth. He says, science says that we are spinning on the Earth's axis about 1,000 miles per hour. If the Earth's core being molten metal, essentially liquid, then the core must, by the theory, traveling in the opposite direction as the crust of the Earth. If this is true, unless the Earth is solid, then you are right. I'm not sure exactly if that's a question or a statement. Any comment on that? I'm not really sure if I'm if I'm understanding it correctly.
Well, I would say this. I don't know about the core of the Earth. There are arguments either way. Some say it's solid, some say it's liquid. We just don't know for sure. And I know they're still continuing to study that. I would say this, it really doesn't make a difference in the heliocentric versus geocentric argument, because the same inertial forces that control whether that core is liquid or solid are going to be true in either system. Okay? So, some people try to make a distinction between geocentric and heliocentric by let's say if you throw a ball up in the air in the geocentric system, the ball might move to the left or the right. In the heliocentric system, it's not going to move. Okay, well, that's not true, because you're going to have the same inertial forces in either system. So it really doesn't make any difference whether the core is solid or liquid. You're going to have the inertial forces acting against that solid or liquid the same in either system. So it's basically a question that doesn't really get us anywhere.
Okay, now I have another question for you, and this is more of a result of what's come about since Einstein. Do you think there has been an agenda to frustrate, obfuscate the evidence of scientific observation regarding geocentrism?
Oh, yes, definitely. Yes. And it goes back to what we were saying before. If what I'm saying about Michelson-Morley is true, about Sagnac is true, about Michelson-Gale is true, and all the other experiments, Arago, Fresnel, and the whole history of scientific empirical evidence for geocentrism is all true, well, then what does that mean? Well, that means that we've been living a lie for 500 years, a lie that has permeated our culture in unprecedented respects. And it affects every science, every art, every culture, every thought we think. Because if we are still, if we are fixed in this universe, that is one of, I mean, it's just as big as it was in Copernicus's time for Copernicus to say the Earth is moving. That was if you look at all the history books and all the historians who write about this, they say that was the turning point. That was the thing that made modern society, as it developed now through the Renaissance and Enlightenment and to where we are today in modern society. That one thought. Now how could that one thought possibly change so much? Well, if your vision of yourself is in the mirror is now reversed to be something totally opposite of what it was before, how is that going to affect your view of everything? It is going to affect your view of everything else that you do in your life, you see. So that's what they're fighting against. And it's the same reason why when we talked about Stephen Hawking, he said, yeah, I know the evidence points to the fact that the Earth is in the center of the universe, but I just can't accept it. I just can't accept it. Same thing Hubble said. It's intolerable that we would have this as our solution. Why? Well, again, it's because someone with a capital S would have had to put us in the center. It can't happen by chance. And if that means that someone put us there, that means that we're responsible to this person with a capital S.
Doesn't that I'm sorry, go ahead, Doctor. I didn't mean to interrupt.
That means that I am no longer an island. That means I am no longer one who can do certain things and not be responsible for them. That means I'm accountable to someone higher than me, you see. This is the fight that we're in. This is the fight. Why do you think there's all this talk about multiverses and big bangs and dark energy and dark matter and inflation? It's all to keep the Bible under wraps, you see, because the Bible is the one that talks about that someone with a capital S putting us in a special place in the universe. And that means that if it's all this scientific evidence we find is true, and I have no way to explain it away, I have to, as a scientist, submit to it. And if I submit to the scientific evidence, I have to submit to the ramifications, philosophical and metaphysical ramifications of that scientific evidence. which puts me as a creature created by the great creator. And that means I'm responsible to him.
And this agenda that is out there, it seems to be driven by an elite that wants to keep this information from forming minds, young minds in universities and colleges all around the world. And in that sense, is modern science corrupt?
Yeah, modern science in many ways is corrupt. I have a whole chapter on that in my book, and I show not only in the field of cosmology, but also cosmogony, medicine, anthropology, paleontology, psychology, sociology. I mean, all these disciplines are controlled by money, by people with cultural agendas, by atheism, and you go down the road and see how all of them, and because of all these pressures that these scientists are under to conform to the status quo, and the status quo basically is atheism, well, they're going to interpret the data accordingly. And that's why my big thing here is the Copernican principle. That's the lens, if you want to call it, that they see the data through. As a matter of fact, we were talking about Lorentz and Einstein, and when they were trying to answer the Michelson-Morley experiment. Well, they came up with every conceivable answer to explain the Michelson-Morley experiment, except the very one that's the most obvious, and that's that the Earth is standing still. Because they were so influenced by the engine of modern science at that time that had accepted as dogma Copernicus's principle that the Earth was moving, that they were so blinded by it that they couldn't see anything else. And it's interesting when Ronald Clark wrote the biography of Einstein. He's one of the major biographers of Einstein. He says he was the one that admitted that the Michelson-Morley experiment, in several places in his book, it's 800 pages long, but in several places he admits, he says, after the Michelson-Morley experiment, we had three basic choices. And one was special relativity. The other was that the Earth was moving with the ether. And the other was that the Earth was standing still in space. And then he closes that sentence and he says, but that was unthinkable. That was unthinkable. In other words, we know that that's a possible solution scientifically, but we just can't go there. We just can't go there because we know the ramifications of it.
We can't say anything or we can't say anything that would give any kind of credibility to sacred scripture, right, Doctor?
Yeah, because the whole agenda since the time of Darwin in the late 1800s has been to put the Bible in a box, basically, and now use empirical science to prove that the Bible has been wrong all along. And if Copernicus showed us that the Bible was wrong about the Earth being still in space, being fixed, well, then what else is the Bible wrong about? Well, hey, you know what? The Bible can be wrong about
morality. Anything.
Yeah. Wrong about morality. As a matter of fact, there's a whole hermeneutic that has been developed called historical criticism that does nothing but try to undermine the Bible and give us rational scientific explanations for why we can have immoral behavior.
Raymond Brown, thank you very much.
Yeah, that's one of them.
Yeah.
And that includes whether it's homosexuality or marriage and divorce, adultery, drugs, psychology. I mean, you go down the list. All of these have been attempts to undermine the clear moral propositions that are put in Scripture. And the one basic impetus they have had to do this was what Copernicus said about the Earth moving in space. Because if you can prove that the Earth moves in space, or if you think you can prove it, then basically you have undermined a basic tenet of Scripture that has been believed for 1,600 years prior. You have shown that the Bible is an error, and if it's an error in one place, then it's an error in numerous places. And basically then, the Bible is no longer your authority. The church is no longer your authority. you have now succumbed to scientism as your authority, and that is where you base your whole life. So that's what is at stake here. And the men of Einstein's generation and Lorentz's generation knew that. They knew exactly what the implications were. And they tried for 25 years, as I said, from the first time that Michelson did his experiment, to find a solution. And until Einstein came and turned science upside down and made it a haunted house of mirrors, did they have a solution to get them out of this corner that they were trapped in.
You want to take a glass of water there, Doctor?
Yeah, give me 2 minutes.
Take your time. We're gonna take a little break here, folks. We only have about 35 minutes left, but we'll just play a tune or two, and maybe just one tune, and we'll be back after this. Okay? Please keep it right here on MSI Radio. Okay, folks, we're back. You are listening to MSI Radio. I'm Live Mike. I'm joined by Dr. Robert Sungenis, and we're talking about geocentrism. Doctor, you wanted to mention CMBs?
Yes, I did. CMB stands for Cosmic Microwave Background Radiation, or the acronym CMB for short, so I'll be using that as I continue in my description of it. This is very important. It's one of the most astounding pieces of evidence we've found so far. You thought the Michelson-Morley experiment was astounding. Wait till you hear this. The Big Bang theory that was proposed in the 1930s by Hubble, Lemaitre, and a few other people required that the expansion of the universe from this little pinprick where it all began required that the expansion of the space or matter or energy within it had to be homogeneous and isotropic. Okay? Now, homogeneous, let's describe what that is. You've bought homogenized milk before, I assume, correct?
Yep.
And that means that there is no fat globules circulating around in that milk, because what they've done is they've shaken it up to a point where all the fat in the milk is distributed evenly, and you can't tell one side of that milk carton from the other if you look at it through a visible plastic container. It's homogenized. That's what is required from the equations of the Big Bang theory, that they had a homogeneous universe. In other words, it couldn't be patchy. You couldn't have one section of the universe exploding more than the other section. You couldn't have one section of the universe creating more matter and energy than the other section. You see, it all had to be even. It had to be homogeneous. All right. So when Penzias and Wilson in 1963 discovered the cosmic microwave background radiation by actually, it was inadvertent that they discovered it, but nevertheless there it was. They discovered that it had a temperature of about 2.75 degrees Kelvin, and they understood it to be homogeneous. That is, that there was no difference in the temperature of the universe in one section as opposed to the other. It was all 2.75 degrees Kelvin. All right? Then in 1978, and this was the very year that Penzias and Wilson had won their Nobel Prize for discovering the CMB. In 1978, that same year, someone did some analysis of the sky and found out, wow, we're not finding the universe to be as homogeneous as we thought it was. There seems to be some inhomogeneity out there. There seems to be some anisotropic quadrants in the universe that we didn't calculate before, and these aren't predicted by the Big Bang theory, at least not.
Can you explain that word? That just means that things are irregular, right?
Yeah.
Okay.
Yeah. These are the words they use in their papers now, so I have to use them.
Oh, fair enough, Doc.
Yeah, but they're all basically the same thing. It's either smooth or not smooth. Okay, that's basically what it all boils down to. We have a smooth universe or we have a patchy universe. Okay? The Big Bang wanted a smooth universe, but they began to see a patchy universe up there in the sky. So, about 10 years later, they sent up a satellite probe called the Kobe probe. COBE is the acronym for Cosmic Background Explorer. COBE took pictures of the universe, and pictures that came back were a lot of it was homogeneous, but a lot of it was patchy. Okay, so there should be no patchiness there. If the Big Bang mathematical equations were correct, there should be no patchiness at all. Right? But there was patchiness. So they're scratching their heads saying, how are we going to explain this? Our Big Bang theory isn't working. So they sent up another probe in 2001 called the Wilkinson Microwave Anisotropy Probe. There's that word anisotropy again, and all that means is, it's either smooth or not smooth. Anisotropy means it's not smooth. So they're looking for unsmoothness in the universe because COBE already came back with a report that it wasn't smooth. And the Wilkinson probe in 2001 was 10 times more sensitive than the COBE probe. And lo and behold, what did Wilkinson come back with? Well, Wilkinson came back with not only the same thing COBE said, but even more pronounced. It was even in more detail now. There was patchiness in the sky. And there wasn't only patchiness in the sky. Now they were finding that this patchiness was oriented in such a way from the edge of the universe to the very earth we're standing on. This patchiness had an axis that stemmed from the edge of the universe all the way to the earth. Okay? And they divided this patchiness into two segments. One they called the dipole, and the other they called the quadrupole. And you can divide it even further, the octopoles, and further. But all you have to know for this is they divided the CMB radiation into two segments, the dipole and the quadrupole. And the dipole pointed to the Earth's equator, and the quadrupole pointed to the Earth's and Sun's ecliptic. The ecliptic is the path that the Sun goes through the stars around the Earth. Okay? In other words, if you can put this in layman's terms, the whole universe, as described by the presence of the cosmic microwave background radiation, was oriented around our little Earth. Okay? Now that's significant. That's very significant. Because the Sun-Earth distance is 93 million miles. Okay? Well, the diameter of the universe is supposed to be 93 billion light years. Well, that means that the Sun-Earth distance, and that's the distance that makes up the difference between the equinox, that is the equator, and the ecliptic. Okay, that little angle there is 23.5 degrees wide. All right, but that little angle and the distance between the Sun and the Earth of 93 million miles is 1 quintillionth the size of the universe. Okay, but yet they found by this probe that the whole universe is oriented around that 1 quintillion distance between the Sun and the Earth.
Man.
That is amazing. Okay?
Yeah.
Absolutely. Now, in the literature,
it doesn't speak to a designer though, does it, Doctor?
No,
of course not. Of course not.
Okay, so the literature in this, Max Tegmark was the first one to find this in 2003. He is an astrophysicist from MIT. Now you can't get any more higher than that. Okay, he found these anisotropies in the CMB, and he was absolutely amazed. And he just made a sort of a note about it in his paper, and then somebody else picked up on it from the University of Michigan, and they have a very sharp team up there, Schwartz, Hutterer, Longman, who else is up there? Longo, very sharp guys. They did an extensive study on this cosmic microwave background radiation, and they confirmed that it was oriented around our little Earth, our ecliptic and our equinoxes. And they were astounded. They had no explanation for it. They wrote 3 sets of papers over the course of maybe in the next 8 years. And at their final paper in 2012, they said, this is not going away. This is staying here. We cannot explain it away. We have no explanation for why the whole universe even knows we exist, much less has oriented itself around our little Earth. Okay, they write this in their papers, and I quote them in my book. Then there was another group, Kate, I forget her last name. Kate. Anyway, she wrote a paper with another astrophysicist in 2004, and they put a name on this orientation of the universe with the Earth. They called it the axis of evil. So that's interesting. Wow. The axis of evil. All right. Now, I mean evil. E-V-I-L. That's what they call it. All right. Mm-hmm. And Kate Land was her name. Yeah, Kate Land, L-A-N-D. And so now, if you remember, back in 2004, I think the United States was invading Iraq, and Bush termed the people that were against the United States, including Iraq, I forget who else was involved, Iran, Syria, whoever. They called it the axis of evil. All right. So Kate Land and her partner picked up on this term and said the axis of evil was this axis that was stretching from the Earth to the edge of the universe, around which the whole universe was oriented. All the cosmic microwave background radiation that was between us and the edge of the universe was oriented around this axis. Okay? So, and they were in consternation again. How could this possibly be? This goes against the Big Bang Theory. It puts the Earth in the center of the universe. As a matter of fact, that same professor I talked about before, Lawrence Krauss, wrote a paper in 2006. It was about a totally different topic. He was talking about the quantum field. And then at the end of the paper, it was just a casual paper, but still, it's coming from him. At the end of the paper, in the last two paragraphs, he talks about the cosmic microwave background radiation and what they discovered from this 2001 Wilkinson probe. And he says, well, that means we're in the center of the universe. Now this is a guy who's a heliocentrist. He's a atheistic, a modern Big Bang cosmology professor. And he says, yeah, it looks like this cosmic microwave background is putting the Earth in the center of the universe, or our whole physics is wrong and we need to revamp it, you see. So he leaves himself that out. That, we could be wrong about everything. So we just have to start from square one, so to speak. And anyway, and I quote him in my book, and as a matter of fact, he's in our movie. We interview him in our movie. So,
Go ahead.
One more thing on
Sure.
this, and then you can go and ask a question. Mm-hmm. So they get this evidence from the 2001 probe, and they're scratching their heads. They don't know what to do with it. All these papers are coming out. They have no idea how to explain this. And so they say, okay, let's do this. Let's send up another probe. This is how you solve problems in NASA and the European Space Agency. You send up probes, hoping you're going to find something different, right? Excuse me. So they send up this probe in 2009 to confirm or deny what the Wilkinson probe found in 2001. It's called the Planck probe, after Max Planck, the very famous physicist. It's up there for 4 years, mapping the universe, okay? And it's very sophisticated machinery. Probably one of the most sophisticated pieces of machinery we've ever sent up into space. It took pictures of the universe, just like the Wilkinson probe did, just like the Kobe probe before that did. And only it was now 10 times more sensitive than the Wilkinson probe. And what did it find? Take a guess. It found the same thing that the Wilkinson probe found. And it found the same thing that the Kobe probe found 20 years prior. Okay? And this evidence was just released on March 21st, 2013 by the European Space Agency. And they were in cooperation with NASA. Alright? Now, do you think the European Space Agency at the news conference is going to admit that the Copernican principle has been falsified?
Of course not. They can't. They can't. Of course.
Yeah. So what they do is they write a report and they say, well, there's certain anomalies in this cosmic microwave background radiation that's been mapped by the Planck probe that we can't explain. And, and some of it actually goes against the standard model of cosmology. And, they made 3 statements like that basically say, yeah, we got a problem, but we're not going to give you the implications of that problem.
Vague generalities. They don't really, yeah. Mm-hmm.
I'm here to tell you what the implications are.
Mm.
They're not going to tell you. I'm going to tell you because I don't have a bias. I'm going to tell you exactly what the problem is. The problem is that the Planck probe justified the Copernican principle. You see, it defied also the cosmological principle that out there in space, everything is homogeneous and all exploded from this one little point. Now, you can't explain that from these irregularities in the CMB up there.
And the balance between the expansion and the gravitational pull.
Yeah, that's
the rate
right.
of expansion. Yeah.
Yeah.
That's the formula that you said earlier someone was spent their entire life trying to find the formula, but they couldn't, yes?
Yeah, that's right. And this puts another wrench into the works of that, because now you have to explain where these anisotropies come from. Where does this inhomogeneity come from? Well, now they're trying to say, well, it's good that we have these inhomogeneities there because that means we had differences in temperature enough to form galaxies and all this. So they're now trying to patch it all up by integrating it into their Big Bang theory of homogeneity. Okay? But the fact is, even if they did that, they can't explain why the cosmic microwave background radiation from the edge of the universe is oriented around our little Earth. You see? That's what they can't do. It's like the pink elephant in the room. And you wash up the elephant, you say, oh, doesn't that look pretty? Yeah, but the pink elephant's still there, you see.
Yeah.
Because the CMB is pointing right to the Earth.
You can't explain it away. You cannot.
Yeah. So that's where we're left. So that's why this is very important. So on the larger scale of things, cosmic microwave background radiation and what they found about it puts the Earth at or near the center of the universe. Okay? That's admitted by them, as I just quoted from Lawrence Krauss.
And this is the most recent experiment that we have.
Yep.
Yeah.
It's the most recent probe that we have of the whole universe. It maps basically the whole observable universe. And that's what we come up with. So on the larger scale, we're now shown by the scientific evidence to be at or near the center of the universe. And then you have the Michelson-Morley, Michelson-Gale, Sagnac, all those experiments that were done prior to Einstein's invention of special and general relativity that show that the Earth is not only in the center, but it's not moving. It's not moving.
Yeah.
Okay.
It's perfectly fixed. There's no movement at all. It's just stationary, correct?
Yes.
Wow. Now,
it makes sense.
Yeah. Now, once geocentrism starts to pick up steam and more people get on board because of the scientific evidence and observation, what do you suppose the consequences will be as a result?
Well, it depends. If we can gain enough steam, as Kuhn talks in his book, he's a professor from MIT, a scientific historian, and he said that every once in a while there's a paradigm shift. And that can occur like once every 50 years and once every 100 years. And I think if it catches on and people are honest with the scientific data, and I think the groundswell of people who hear this evidence are going to put pressure on them to be honest with the scientific data and not try to shove it under the rug. If that's the case, we could be headed for a very paradigm shift that Kuhn talked about in his book, a revolution in science, no less, where now we cannot produce answers to the data any longer that satisfy the hungry mind who wants to fit everything together as perfectly as he possibly can and not have any strings on it. We're going to reach a point where we have no longer the answers that we need in order to keep the present paradigm existing, and there's going to be a total shift into a new paradigm. I would predict that if this new evidence gains a foothold and generates enough interest, and we get enough important people talking about it, we could have a paradigm shift within the next 20, 30 years.
I hope so. Now, I'm going to ask you two questions, real quick. Well, one question, just a fast answer. Is it possible for corporeal sentient life to exist on other planets given the fact of geocentrism? In your opinion?
My opinion, no. There is no life out there on other planets. And as a matter of fact, when we interviewed Max Tegmark for our movie, he said the same thing. And he's an atheist. He said if you add up all the possibilities out there of life on other planets or whatever, he said that the equations always show zero as a possibility. So now that's not coming from me. That's coming from him. And we asked him that specifically. So that's from a scientific vantage point. So the philosophical and theological vantage point, I would say, yeah, the possibility of life being on other planets is nil. Absolutely.
Okay, now let me ask you this question. There's been a lot of talk starting back in 1981, 1983 about a very large body at the extreme outer edge of our solar system, maybe around the Oort cloud, who knows. You know, some people are calling this thing Planet X, other people Nibiru. What do you think of the possibility that we live in some kind of a binary star system where there is maybe a brown dwarf out there that likes to take a trip around the Earth every 3,600 years or so? Any idea about that? Any thoughts about that?
Yeah, I've heard about that. I really don't get into that because it's just all speculation.
That's right. I just wanted to ask. Doctor, would you mind if we had a guest come on and ask you a question in person?
You mean right now?
Yeah, is that okay?
Sure, no problem.
Okay, now this fellow's name is Shaziz, and I think he's going to kill me if I don't give him a chance on the mic to speak with you. So, okay, folks, we're just going to take a real quick break, and I'll get Shaziz back, okay? Okay, folks, we're back, and we're joined by Shaziz, who'd like to ask Dr. Sungenis a question.
I'm trying to wrap my head around this mechanically about the universe traveling around the Earth, and the Earth being the center point. You know, it's just like on a bicycle wheel, you have an axle, and so with that said, you know, the axle is the center point of the whole deal. So, if our Earth was being traveled around by the entire universe, then there has to be some center point, some axis point, otherwise you have no rotation. And so with that said, if the Earth's core is a molten liquid metal, then it should be, in theory, by traveling in the opposite direction of the rotation of the Earth itself, which would have to occur because of the centrifugal force and all the gravitational pull of all the extra bodies around us. We would be spinning, but if we were on the axis point and there was no center point, such as the molten metal core, and we were a solid object, then it would be the equivalence of having a bearing in your wheel that would literally be froze up, and therefore you wouldn't have no motion. What do you think?
Yeah, that's a possibility. You would actually get some lubrication for the Earth to be rotating in the heliocentric view if you had a liquid core. I think the point of fact is that we don't know whether we have a liquid core or a solid core. So, I mean, everything we're saying here then would be speculation as to how that would all occur. But as I said before in the beginning of the program, it really would make no difference between the heliocentric and geocentric frameworks because you would have the same inertial forces acting upon that liquid core or solid core in either system. So either system would have to explain its mechanics based on that.
Well, I understand what you're saying, but what I'm trying to get at, because the question I'm trying to ask would either prove or disprove what it is that you're saying by the simple fact if it was solid, if the Earth was solid itself, then there would be no motion. There would be no axis point. If the Earth's core was liquid, then would it be that the expanding Earth theory could be possible due to centrifugal force and all the gravitational pulls of all the extra bodies that are spinning out? You see what I'm saying? When you
let me ask you a question. You said if the Earth were solid, did I understand you correctly to say that would disprove the geocentric theory?
Well, to me, it would state that there would be absolutely no motion, because otherwise then we would have to rip apart. If centrifugal force was true and we were a liquid core, then the Earth could in theory be expanding due to the pressure of all the gravitational pulls of all the extra bodies that surround us, and so literally we would be going outward, if you understand what I'm saying. But with no center point, you can't have rotation.
Yeah, I think what you're saying is the centrifugal force of a rotating universe would rip the Earth apart if it were solid. Is that what you're saying?
Well, at some point, it's like stretching a rubber band out. One or two things is going to happen. Either it's going to collapse in on itself, or the rubber band is eventually going to snap.
All right. Well, let's look at it from another vantage point. Let's say that you are in a car and you're going 50 miles an hour, uniform speed. Do you feel any centrifugal or any inertial forces when you're moving at that uniform speed?
Well, not while I'm in the car, unless I stomp on the gas, and then I can feel the G-forces suck me back in the seat.
Right, is exactly the point, okay? So in other words, as long as the centrifugal forces and the Coriolis forces are uniform, there's going to be no there's going to be no way to feel any force. The only reason you feel force is when you change direction, or you go backwards, accelerate forwards, or you decelerate backwards. That's when you're going to feel the inertial forces. Now, the reason I'm mentioning that is because if the universe is moving uniformly around the Earth, well, then there's no tendency then to break apart the Earth, even if it was solid, because the inertial forces are uniform. If the universe were to suddenly accelerate or decelerate, yes, then you'd have a breaking apart of the Earth, because the inertial forces are to such an extent then that they would affect the Earth and break it apart.
So in this scenario here with the universe going around, we
don't have too much time, Shazaz. This will be the last question, okay?
Okay, would it be that some of the objects out there are actually moving faster than, like, let's say the moon? The moon travels around the Earth. Otherwise, if everything's stationary but spinning as like a top, then everything's moving together, and wouldn't we not have, like a sunrise, a sunset, or a moon coming up or down?
No, the geometrics of the geocentric universe are exactly the same as in the heliocentric. This is something people really need to understand. Most people go back to, Ptolemy's model of the geocentric universe and say how different it is from the heliocentric, but it's not really. Tycho Brahe was the one who developed Ptolemy's system into an exact reciprocal of the heliocentric. So all the geometrics of the sun rising, the moon going around are all exactly the same in both systems. So you really can't attack it from a geometric argument. You have to look at it dynamically, and that's what I was just trying to explain dynamically, that you wouldn't notice any difference since there wouldn't be any deceleration or acceleration of the universe against a fixed Earth.
Doc, we only have a few minutes left. Do you have any final thoughts you'd like to impart to our listening audience?
Well, I would encourage anybody who's interested in this to get a hold of our books. The first volume, actually it's in 3 volumes now. It's on a 6x9 hardback framework, so it's easy to handle. And the first 2 volumes deal with the science, and we get into every scientific aspect of geocentrism that we could think of, because we try to cover every area, so we leave no stone unturned. And we covered a little bit of that in this 3-hour session now. but there's much more in there. And my co-author is he was actually a general relativist. He's a physicist with a PhD, and he taught general relativity for many years at Stevens Institute. And he is my co-author, so he backs up everything I say, and he uses a lot of math and calculus, and so it's all there for the scientist who wants to delve into this. And then in the third volume, which is about almost 600 pages, we cover the history of the Galileo issue, the church's dealing with Galileo. We cover all the scriptural passages that are used for geocentrism. We go back into the church fathers, and we get all their quotes about geocentrism. And as a matter of fact, I just want to say that the fathers, the church fathers from the Catholic Church, were in absolute consensus about geocentrism. And this wasn't in a vacuum. This was against the heliocentric system that was first developed by Pythagoras in the Greek culture. And he was opposed by Aristotle, who believed in a geocentric universe. So even back then, with the Greeks, there was a controversy about this. And the church fathers sided with the geocentric. And why did they do that? Well, because the scriptures had taught geocentrism in about 24 passages. And we cover all those passages in graphic detail in our book. We go into the original Hebrew and the Greek to show people what these documents actually said. And we use logical argument to sustain why the church upheld the scripture as telling the truth about this cosmology. And then, of course, we get into the whole Galileo affair with the popes and cardinals, and up until the modern day. When John Paul II gave his speech in 1992, seemingly exonerating Galileo, but not so when you look very closely at what he said in that 3,000-word speech that he gave. So we cover the whole gamut in volume 3. And then we have a CD-ROM that has all 3 volumes on it, and it also has many, many animations which describe in graphic detail all the things I'm talking about here about the geometry and the dynamics and the Ptolemaic universe, the Copernican and all this, and you can see it all for yourself. The cosmic microwave background radiation, the Michelson-Morley experiment, we put that in an animation so you can see exactly what's going on. These are graphics that are nowhere else found in the world, believe it or not. We are the first ones to make some of these graphics, and they're very explanatory about what I'm saying here. So I would encourage anybody who's interested to get the books. And we do have a movie coming out called The Principle. And The Principle, it's titled that because it's speaking about the Copernican principle, the basic cultural motif of all our modern society today. And that'll be coming out February or March of next year.
All right, there you have it, folks. Dr. Robert Sungenis, you have been an absolutely brilliant guest, and I want to thank you ever so much for being here. I sincerely hope you'll come back and talk again sometime, okay?
Yeah, no problem, Michael. Thanks.
Yeah, I'd like to talk to you, if we could, about authority and scriptural scholarship and authority. That's something that I think there's a lot of people in this audience that would appreciate, okay?
Yes, very much so. I'll be glad to do that for you.